Re-Raid 1. One of the most bizarre aspects of space is black holes. They are not objects. Instead, they are created by extreme space-time warping. Because of this warping, a lot of strange stuff happens around them which will alter their perception of how the universe works around them. You might not believe some of this stuff, but solid math backs their existence and properties. We also have increasing evidence that math is accurate through observations in our universe. As we explore the science behind black holes, what happens around them, and what may allow us to escape the most inexorable prisons, please join me. I hope you will like this video and subscribe to it. There are many sizes of black holes. The smallest black hole that has been observed is approximately 3.8 solar masses. Black holes with billions of solar mass are also found on the other end of the scale. These massive black holes are so large that they could easily be incorporated into the entire solar system by the size of their event horizon. The creation of black holes today is the last stage in the lives of massive stars. This star is basically balanced under two forces when it is born. Gravity pushes its mass toward the center. The star's depths contain hydrogen atoms that are crushed against each other with such force that they form helium, a denser element. The new atomic structure requires less energy than the two separate hydrogen atoms. Therefore, more energy is released. This energy is called the second force. This energy radiates out of the star's center as heat and light. It counteracts the gravity pushing in. The star will be stable in the state until the star runs out of hydrogen fuel. If the star is large enough, when hydrogen runs low, the star will combine newly formed helium into denser materials like carbon, neon, and eventually oxygen and silicon. The star then begins to fuse iron. Iron has a problem. It doesn't conserve any energy, so it can release all the energy. It grows larger by sitting in the center of the star. The scale quickly dips, as there is no energy to push back against gravity. Although the energy from this collapse is amazing, the force depends on the original star mass. The star's mass is like a hammer hitting an anvil. It then hurries down to the core with such force that we call it a supernova. From the crackback, matter and energy are blasted across the universe in one of the most powerful explosions, which produces elements heavier than iron and even uranium. What is left of the star? Well, it depends. It all depends on the mass and force of the blow of the star. If it was too small, the neutron star is left. This is a tiny ball of matter measuring only 25 Kelvin in diameter and densely packed with mass, which equals 1 million Earths. If the mass and force were large enough, the physical world as we know it breaks down and leave us with a black hole. The black sphere that you see when you look at an image of a dark hole is not a black hole. Scientists believe that a black hole is smaller and denser in real life than a neutron star. It is actually likely infinitely smaller and infinitely dense than a neutron star. This is because the singularity emits forces that can warp time and space. We don't know. The event horizon is what makes it impossible to know. Gravity is a property of all objects that have mass. This has been known since Newton's time. Carl Schwarzschild, a contemporary of Einstein's theory of general relativity in 1915, suggested that objects could exist that are so large that they can create enough gravity for light to escape. Even massless light photons could not escape, so nothing could. If you see a photograph of a black hole, you don't actually see the black hole. The event horizon surrounding it is what you are seeing, the line at which gravity has become so strong that light cannot leave. There is only darkness. Its effect on space is one thing, but black holes also have an impact on time. Einstein said that space and time are interconnected and that mass warps space-time. The singularity's infinite point in mass expands space-time to the point that time stops. The event horizon is a place in which space and time cease to exist. An outside observer will be able to see the interesting phenomenon of matter falling into a black hole. Their perspective is that as the matter approaches a black hole, it will slow down until it reaches the event horizon where it will stop completely. It will not cross the event horizon, and there won't be any satisfying absorption. Instead, you will see the matter gradually dimming until it is no longer visible. Astronomers and physicists weren't sure if black holes existed when they were first proposed. The first observation of a black hole was made 40 years later. Scientists discovered a Cygnus object that appeared to emit a lot of X-rays in 1964 using new X-ray satellites. Scientists couldn't see the object, however, which was strange. They were surprised because, if the object was a star, it should emit visible light along with X-ray radiation. This object was called Cygnus X1 by scientists. As telescopes improved, scientists noticed that Cygnus X1 had formed a binary orbit with a star in its system. This helped them calculate its mass. This invisible object was 15 times larger than the Sun, according to scientists. Scientists realized that the densest neutron star had a mass limit of 3 times the Sun's, and this made it most likely to be the first black hole ever discovered. We have since discovered many black holes. We have taken photos of supermassive black holes at the center of galaxies. This is how X-rays can detect black holes. Although black holes don't emit visible electromagnetic radiation, the X-rays they produce actually come from their accretion disks. This is where infalling material heats up to millions of degrees Celsius by intense friction. The black holes have no infalling matter and are therefore virtually invisible, with no bright accretion disk to identify them. The science of black holes remains a rapidly developing field in physics, and there are still many things to discover. You may be wondering if a dark hole can ever cease to exist. Or will it continue growing until there is no more matter or radiation in the universe? This would appear to be the case. Stephen Hawking, a physicist, suggested in 1974 that there was a way energy and mass could escape a black hole. To understand why, however, we need to look at some very strange theories. Let's examine the principles of quantum mechanics. Let me first ask you a difficult question. What is nothing? For a second, imagine a space patch with nothing in it. It is free of radiation and atoms made from space dust. It is empty of any atoms of space dust, radiation, or other matter. But is it really there? Well, no. This is because there is something fundamental that exists in the area. We can see it when a beam passes through it. You will be familiar with the properties and functions of light. Light is actually waves of magnetic and electrical charge, which are continuously propagating forwards in a straight line. Let's look at the word wave. Waves in the sea are the result of the propagation and movement of energy through water. A single water particle is not moving in any direction, but it does pass energy to other atoms. This energy moves towards the shore in a steady motion, all the way to the coast. A sound wave is similar to a sound wave. It moves by passing energy among air particles. Each particle only moves a little bit before becoming energized and then passing the energy on to the next one. Have you ever wondered what waving is in the vacuum of space? This suggests that there is a fundamental thing that exists in everything, a fabric that creates all reality. This something is referred to by quantum physicists as a quantum field. Although quantum fields can be difficult to grasp, they are essential for understanding the fate of a black hole. How do quantum fields and exploding black holes relate? Hawking's paper posited that black holes would slowly release energy over time in small quantities. According to Einstein's famous equation E equals square mc, energy and mass are two expressions of the exact same thing. This inevitably leads to a decrease in the mass of the black hole. As the black holes shrink, the rate at which energy is released would increase, becoming faster and more rapid until, in the final moments of their life, it would release an enormous amount of energy before disappearing completely. How could this be? As it is known, radiation cannot escape an event horizon. This makes it impossible for radiation to leave the horizon and cause a black hole explosion. This strange answer relies on quantum theory, which is completely contrary to our daily experience. If it is true, I hope that you are prepared to see the universe as a lot strange than you thought. To understand Hawking's theory, we must first understand quantum fields. Light moves like a wave through any space. This means that light can move through any space. This fundamental fabric of reality is called a quantum field by scientists. They believe there are many quantum fields that overlap each other and cover every patch of the universe. Each quantum field is a specific type of something. One field could define all electrons, while another field might define quarks that make an atom. The quantum field is quiet where nothing can be found. It can be compared to a string of guitars that have not been played, or a graph with a zero value. The quantum field is always resonating wherever energy or mass can be found in time and space. When the resonance reaches a certain quantity or threshold, the universe will express that as an electron or photon. Important to remember that the resonance is not merely reacting to a particular piece of matter. It is actually the matter. An electron is simply a section of the quantum field that defines electrons. This holds true for all energy as well as all matter. Einstein says that energy and matter are just two sides of one coin. Everything you see is made up of resonating quantum field and nothing else. This theory depicts the entire universe as a song that is being played on these fields. I find this beautiful. Why is this important? This is why it is important to define the universe this way. A quantum physics idea called Heisenberg's uncertain principle means that sometimes the strings of the universe can start to strum. This aspect of quantum physics is important to understand. It's impossible to know enough about very small objects at the atomic level. For example, you cannot determine both the location and direction of travel for an electron, because electrons are so tiny. Once you attempt to determine the location of one, they bounce off any measuring device you use to measure them. This means that you cannot be certain of their direction of travel. This principle states that if you don't know the direction of an electron, you cannot determine its location. This is due to fundamental laws that govern the nature of the universe. Heisenberg's uncertainty principle states that you can't know all about particles at a subatomic level. This principle becomes a little more complicated when applied to quantum fields. Quantum fields can fluctuate all over the place, and according to Heisenberg's uncertainty principle, particle and antiparticle pairs can pop in and out. Although the how and why are complicated, it is clear that the universe allows this as long as they exist for a short time. This is governed by uncertainty relations. This might seem absurd. Matter doesn't just appear. We'd have noticed it by now. Hendrik Casimir performed an experiment that suggested that this could actually occur. Casimir placed two plates of conductive steel close together so that small virtual particles could only exist between them. This limit on the number of virtual particles that can pop into existence was important, because all kinds of particles can pop into existence outside the plates. There was an effect on the pressure on each side of each plate. Theoretically, more pressure exerted by larger numbers of virtual particles outside the plates should cause the plates to push together. This was the case in the test. It is possible to believe that particles appear out of thin air, defying the laws of conservation. That would be correct. To balance the equations, every time a virtual particle is created, another particle also appears to pair up with it. The matter particle is the one that is being viewed, while the antimatter particle is the other. Our bar chart shows a 1 and -1, keeping the overall number at 0. The universe is happy. These fluctuations in the quantum field crash into one another and annihilate them, thus removing them from existence. Side note, there is a theory that antimatter is simply matter moving in the opposite direction throughout time, but that's another level of strangeness we don't need. It is important to remember that quantum fields are always resonating and canceling one another out. This is why empty space is essentially empty. But what if some of these fields stopped resonating at all? This is where black holes are. Black holes are a little like your thumb touching the string of the universe's guitar. Certain resonances in quantum fields are affected by their event horizons. Hawking imagined drawing a line through time in a space where a black hole was formed. Hawking imagined a quantum field that resonated along the line, stretching from the beginning of existence and into the future. All was normal before the birth of the dark hole. All quantum fields resonating freely can cancel one another. Hawking noticed that some pulses were missing their opposite numbers after the black hole's emergence. After the formation of the black hole, Hawking began to see the math and realized that not all was being canceled. He found resonances outside of the event horizon that perfectly matched the thermal radiation that was flying into space. Radiation is energy. Energy cannot be created from anything. The black hole created this radiation and would be responsible for its consequences. Each piece of Hawking radiation would correspond with the same amount of energy that was lost to the black hole. This would eventually make it virtually null. Hawking radiation, if it is real, would be like money appearing spontaneously outside of a bank while the money inside its vault disappears. It is also difficult to prove, as Hawking predicted that this radiation would be much colder than the background cosmic radio that fills the universe, and would have a wavelength twice as long as the black hole's event horizon. We are unable to detect this type of radiation because some black holes have event windows that are larger than solar systems. It would only be possible to see it if the universe was completely dead and cold. Then there would be no other way. This would likely mean that we wouldn't be able to detect it anymore. Despite all the objections, Hawking radiation's math seems sound. Scientists have taken steps to prove it in the laboratory. Researchers at the Technion Israel Institute of Technology came up with a way to circumvent the difficulties of measuring a black hole in real life. This was done by creating an analog sonic black hole that would have the same properties as a real black hole. Because sound is slower than light, it was easier to create a medium that moves faster than sound. It moves in the same direction that sound's waves travel, so it cannot escape. It is interesting to note that Hawking's math works for these sonic black holes just as well for gravity-based ones. Therefore, Hawking radiation should be detected from it. The researchers repeated their experiment 97,000 more times in 124 days of continuous experimentation and found multiple instances of Hawking radiation. This confirmed Hawking's predictions about how his radiation might behave. While this doesn't prove Hawking radiation exists for black holes, it does suggest that Hawking might be right. Hawking radiation may be real. What if you were to fall into a black hole? It is unlikely. If you waited to the very end of the universe, however, the black hole might just emit Hawking radiation until all the energy and mass that made up your existence were gone. Is that considered escaping? This is probably not appealing to you. It's probably best to avoid going in. This is not the only strange thing about black holes. Their existence is a worrying sign of our reality. If you walk on a beach and leave a footprint, it is likely that your foot caused it. This is a clear case of causality, and it's laughable that you even have to say it. The footprint was made by you. You weren't made by the footprint. What if it did? But what if I said that the fundamental relationship between footprint and foot might be more blurred on the cosmic scale than you might think? Surprisingly, evidence suggests that this may be true due to the existence of black holes, Hawking radiation, and other factors. We'll need to start with a principle called relativity. No, that's not relativity. Galilean relativity. Galileo Galilei first described this form of relativity in 1632. It states that there is no distinction between moving at a constant speed and being completely still. Imagine that there are two rooms on a ship and one on land. Both rooms are soundproofed and have no windows. The sea is calm, so there's no rocking. There is only one difference between these two rooms. The first is moving and the second is still stationary. You can see the difference from the inside. It might seem like you would be able to sense movement. You might think that you can sense movement. For example, you could be moving through space at 110,000 kilometers per hour because of the Earth's orbit around the sun. But if you were sitting at home and watching this, you wouldn't have thought you were actually moving. Galileo realized that there wasn't a test that could distinguish between these two scenarios. Galileo discovered that even though a ball is dropped in a ship, It looks straight down from your point of view. It will appear as if it falls diagonally from the perspective of a person standing on the ground. Galileo realized that you can't tell if a planet moves towards you or towards you if all frames of reference are removed, such as being in space. Both interpretations are valid according to relativity. This is something you might have seen if you've ever watched another train pass by your window, rapidly overtaking you. Both trains are moving forwards, but the other train is speeding faster than yours. Because you don't have any frame of reference to compare your motions to, it could appear that you are suddenly going backward. This idea was furthered by Einstein's equivalence principle. He took the idea of two rooms and made an observation about gravity. Imagine you were in a space-filled room and someone began to accelerate your room upwards. This could be done by attaching a rocket to its bottom. The rocket would then feel exactly the same as if it were in a room on Earth's surface. The difference between gravity acceleration and rocket acceleration is impossible to determine, that is, assuming the rocket doesn't shake you. These principles are based on the concept of inertia, which states that objects don't like to move if they're left alone and won't stop moving once it has started. A new force must be applied to a mass if you want it to do something other than what it is currently doing. It will be inert otherwise. It will remain inert. But how would the rocket feel to the man sitting next to it? Perhaps a better question is, how would it feel to us as if we were being accelerated up by the rocket's effects? It isn't expanding in all directions simultaneously, so it doesn't push us along with it. Although this is true, Einstein realized that they felt the same because they were both the same thing. One form of acceleration. There is another type of acceleration. It works in the same way as gravity, but it applies a force to the object to propel it like a rocket. This spinning fairground ride is an example of how acceleration works. You will be familiar with the acceleration that comes from changing your direction. Standing against the wall of the ride will feel like a constant force pushing you against it, even though the ride is spinning at a constant speed. Your mass wants to travel in a straight line at all points in the ride. However, the ride's curvature forces you to change your direction. You feel the force of the struggle between your inertia, trying to keep you doing what you are doing, and the wall trying to change your direction. Acceleration is a matter of how much the earth below you is accelerating you upwards and your efforts to accelerate downwards. This form of acceleration due to a curving path explains gravity best, according to Einstein. His theory was that energy and matter cause warping in the surrounding space, similar to how a ball bends the surface of the taut rubber sheets it is placed on. Curvature is greater for mass. Any object that tried to move through space would be stopped by the curve. John Wheeler, a physicist, said that space tells matter how to move. Space tells matter how to curve. This curve would be quite small for small masses. However, in dense masses, the curvature can become so severe that an object too close to it could not escape it. These conditions are found near a black hole with its event horizon. Going back to the first analogy of the foot and footprint, if a dark hole is a foot, then the curvature space around it is its footprint. It is fascinating to see this all in action and to learn how Einstein reached conclusions that have been nearly universally accepted by scientists even after a century. There's nothing unusual about this. It's not difficult to understand the mechanisms that make this happen. The black hole tells space how to curve and any object that is near it how to move. Based on our day-to-day observations, nothing is out of our reach. Hawking radiation is a very unusual phenomenon when we look at it. It is non-local, which is the most important thing you need to remember for our current video. It does not appear directly from the black hole, but rather from the space surrounding it. To clarify, I don't mean beyond the singularity or the black sphere. It's difficult to define, as space is not known to exist there. The black ball that you see is just the demarcation line between inescapable and escapable curves, the event horizon. Although this is often how the theory is presented, I don't mean right up against it. Sometimes people speak of two particles appearing right up against the event line. The antimatter particle is inside the particle, so it falls in, and the normal particle is outside. However, this is not the case. Instead, the area in which this radiation can be produced is many times larger than the event horizon. This could mean that it could exist at a distance of billions of kilometers. Even though the largest black holes can fit multiple solar systems side by side within their event horizons, it is absurd to think that a photon can exist this far outside of the event horizon. Even in places where there is nothing, it happens. It is not that the black hole is directly responsible for the Hawking radiation. It is actually created by the curvature space created by the black hole, which can occur far from the black hole. However, if this is true, then the results are completely contrary to what we might expect. We'll be discussing that in a moment. Take a look at what happens in this order. The conservation of energy is a process where energy leaves the curvature space and the curvature decreases. As this curvature decreases, the black hole shrinks. This is insane. This is similar to the footprint shrinking and the foot shrinking accordingly. It feels wrong. It's impossible for things to work this way. Yet Einstein suggested that this might be possible. Einstein stated in one of his equations that the curvature of spacetime was proportional to the mass energy of an object. However, the proportion is not causal. This relationship doesn't assume that one is responsible for the other. While we are comfortable with the idea that mass can be changed by changing the curvature, it is equally possible to do the opposite and alter the curvature to change mass. This suggests that mass could simply be a projection of space curvature. If you shine a light on an object, such as your hand, and it creates shadows on the wall, this is because your hand interacts with light. In this analogy, it is possible to believe that you are the hand. Our mass creates the curvature in space around us. But do we know it's not the other way around? Were we just projections and shadows on the wall? Or is there something more fundamental happening in space-time that brings us into existence? Yet we go about believing that we are the real thing. We don't really know. It would be hard for you to distinguish between the scenarios since all you can see is what you actually experience. If relativity taught us anything, it is that there is no way to tell the difference between situations. We can't dismiss the fact that we are in one or the other, or the two may be more connected than we think. This is obviously a theory. Although there are some experiments that suggest Hawking's radiation may be real, there is no hard evidence. This is something to consider. Even if reality does prove to be a projection, it won't affect your day in any way. It won't change the way you think or feel. That's enough to keep you doing what you are doing. It is an example of how, when we begin to look at the fundamental building blocks of reality and explore the strange warping effects black holes have on our nature, it can lead us to question assumptions about ourselves. It's concerning that you might ask the question, "Am I real?" and get an answer of it's uncertain. Black holes have an effect on our reality and our universe. They don't just eat everything in their grasp and then give it all back. They are the ultimate destruction and end of the universe. But what if I told you that black holes might be our salvation? Black holes may be the solution to our energy crisis. They could allow us to travel faster than light speed and solve the problem of energy in ways we didn't even know existed. As I've come to expect, black holes do this by destroying the fabric of reality and completely contradicting my expectations about physics. Maybe we are thinking about black holes wrong. To understand why a black hole ignores the limitations of faster than light travel and to be able to benefit from it, we will need to learn more about black holes. It is difficult to describe the features of a black hole. Because of the event horizon, we can't see the inside of a dark hole. There are three things that we can be certain of about black holes. They have mass and charge, and they have angular momentum. It is possible to wonder what we know about black holes given the fact that there is no light that can illuminate them. These three characteristics are all aspects of the black holes that can be felt beyond the event horizon. This is the key to understanding these three traits. For example, a charge works around a black hole the same way as around other charged objects. This means that a black hole that is charged will attract other objects with a different charge and repel those that are similar to it. It acts as a giant magnet pulling and pushing on the universe. Scientists can track objects as they approach a black hole. By observing how fast certain objects with a charge move towards them, scientists can predict their charge. This is interplaying with mass. You can feel the mass of a dark hole even if it is not on its event horizon. It is actually the primary creator of the event line. It is because mass creates gravitation, and it does so in a linear fashion, according to the same principles as Gauss' law, a theorem on electromagnetism with a gravitational analog. It is possible to determine the mass of an object simply by looking at how far distant objects are from it before they begin to accelerate towards it and how fast they accelerate. You must also consider charge, otherwise, your results may be biased. The last factor is angular momentum or spin. It is possible to detect spin in large mass objects. We will soon dive into the details. Let's accept this as a given and recognize that black holes are indeed very large mass objects. There are many sizes of black holes. The smallest black holes, also known as micro-black holes, have masses that are comparable to our Moon's 7.35 x 1022 kg. It's amazing that they can fit all of this in a tiny space measuring only 0.2 millimeters in size. This really shows how dense a black hole can be. It is smaller than human hair and packs the mass of the Moon. These are just the smallest. The mass of stellar black holes is 10 times that of our Sun, and their diameter is 60 kilometers. Intermediate black holes have a mass equal to 1,000 suns and can fit into a diameter that is 2,000 km, still smaller than the Earth. It is the most massive black hole, with masses ranging between 100,000 and 10 billion times that of the Sun. Also, sizes range from 0.01 to 400 AU. Astronomical units are the distance between the Earth and the Sun. Other than these three features, there is no difference between them. It would be difficult to distinguish two black holes if they were placed in the same space and had the same mass and charge. These three features can have interesting effects on the space area outside of a black hole. It is impossible to travel inside a black hole because time and space break down beyond the event horizon. We think we have a few clues about what must be inside one. The singularity is believed to be at the center of a black hole. This is actually the black hole. We were referring to the diameter of an event horizon when we spoke about diameters. We are not sure what a black hole looks like because light cannot escape it. A black hole's mass is compressed so that it is infinitely dense in space and infinitely small. This is the point for the simplest black hole models, those that don't spin. This is more like a small spinning ring in a rotating black hole. Otherwise, it would be difficult for us to identify spin for a point with no volume. The current laws of physics become very bizarre around a black hole. It is mathematically possible to do very bizarre things if you travel around the point on ideal paths. This has disturbing implications for causality, and it gets into time travel paradoxes, such as the grandfather paradox. It is likely that this only proves that our ideas about singularities may be wrong. The singularity is so small that it will take the successful merger of quantum theory with general relativity theory in order to fully explain what's going on inside a black hole. Unfortunately, we haven't yet succeeded. One day, it may be revealed that singularities are not present in the hearts and minds of black holes. This is all we know so far. It doesn't matter what it is, as it spins like all other objects in the universe. It spins, we pass the event horizon as we travel out of the black hole's center. There is little to no fanfare. Although the event horizon cannot be seen locally, a person outside of the black hole may observe you slow down and stop while you travel through it. However, it might appear that time is still flowing as normal from your perspective. Normal is the case until the universe beyond the black hole stops moving in an instant. This is because the time outside of the black hole travels so much faster than you. This is the essence of relativity. The only way you can prove you have passed the event horizon is by looking outside. This is the photosphere. A zone is located just outside of the event horizon. It contains a point in space that, if a photon enters it at the right angle, it will orbit the black hole in a perfect orbit, much like the moon orbits the Earth. The photon sphere is an infinitely thin area that is filled with photons. This is based on the many photons that have passed black holes over millions of years. You could be instantly fried if you pass through this point. It is here that we discover the zone that interests and excites us, the ergosphere. The ergosphere is the area around a black hole that allows us to detect its spin most clearly. This is because it is impossible to move in this area. You see, mass affects space. This is evident in the curving effect gravity has on the movement of objects through this region of space. It might be better to say that mass drags on the space around it. It brings some of the space with it as it moves through space. Frame dragging is a phenomenon that occurs when a massive object like a black hole spins. Simply put, reality around a black hole spins in a whirlpool that cannot be stopped. Like a real whirlpool, it is spinning around the black hole because everything caught in the ergosphere's frame of reference is being pulled. It's almost like a person moving because they are on a moving walkway. The faster the object spins, the more it happens. This can happen in the ergosphere at speeds so fast that the event horizon space travels faster than the speed of light. To remain at a relative stop point from an outside observer's perspective, you would have to travel faster than light speed in the opposite direction. This is impossible. Isn't that against the laws of physics, though? Isn't Einstein right in stating that nothing can travel faster than the speed of light? Yes, that's correct. However, black holes have discovered a loophole. This rule is only applied locally. You are right there, within your frame of reference. Nothing can move faster than the speed of light. Relativity makes it possible for frames to move away from one another so quickly that objects within them seem to be breaking the light barrier. If you were to move next to them and enter their frame of reference, they would appear to slow down and start obeying the laws again. Although it's quite a strange effect, frame dragging is a real thing. Scientists can measure frame dragging to determine the spin of a dark hole. Roger Penrose claims that there might be a way to exploit it. The rocket would accelerate if it was launched into the ergosphere. After it has gained enough speed, it can fire propellant in such a direction that it pushes itself out of the whirlpool yet again at a faster speed. The Penrose process, also known as the Penrose process, could theoretically provide energy equivalent to 20% of your rocket's mass. This may not seem like much, but Einstein's equation E equals square mc2 states that your 20% mass would generate energy equal to its own times 299,792,458 squared. This is a lot of energy. To harness this immense kinetic energy, you'd need to travel to the nearest black hole, approximately 3,000 light-years away, and then enter its ergosphere equipped with a rocket that can withstand the intense gravitational forces. You would want to locate one that isn't surrounded by an accretion disk, as these can reach temperatures up to millions of degrees and melt solids to make them a gas or plasma. You get the idea. Easy. Okay, this may seem a bit impractical. The implications of faster-than-light travel that black hole frames dragging show us might be the key to breaking the light barrier. We won't be able to go faster than light, but we can convince the frame of reference that we are capable of traveling at these faster speeds. This is just like what happens around a black hole. We might not be able to achieve this feat if we have the black hole's energy. It's a great glimpse at what is possible. Scientists are already investigating the potential of frame dragging to allow for future travel. Maybe that's another topic. This all highlights how the universe is so different than we imagined. Here's something else you might not know about black holes. It is much harder than it sounds to fall into a black hole. It might seem easy. These are the ultimate absorbers and the biggest sources of gravity. It shouldn't be any more difficult to fall into these than it is for other things in the universe. Your intuition might be right, even though you may have believed so. These galactic maws can be difficult to get into, so Einstein thought it impossible during his lifetime. Black holes could even be able to eject you from them at speeds that are close to the speed light. These objects should be easy to access. You might think of it as a slide that becomes steeper as you move closer to the center of a black hole. This is true, but it's also false. Speed does increase to the point that it will approach that of light. In almost all cases, however, you won't find yourself near the center of the dark hole. This is not a strange quirk in time or relativity. It's something that can be observed from any frame of reference. Confused? Don't worry. Let me explain using a real-world example called an accretion disk. At their core, black holes are very simple. According to the no-hair theorem, black holes are thought to be completely devoid of any features, much like a head without, well, anything on it. A black hole's features are often quite plain. They are composed of charge, mass, and spin. As such, they are not necessary for black holes. They don't have to be present for black holes. If mass, such as our unlucky star, stray too close to the gravitational pull of the black holes, it can be torn away by the immense forces at work and sucked towards its center. This matter doesn't all fall immediately into the black hole's event horizon. However, the matter is usually able to coalesce into a flat ring orbiting around the black hole beyond the event horizon. Although eventually all of it will enter, the process can take quite a while. It can take between 100 and 1,000 million years for accretion disks to fully absorb. What is the deal? Why doesn't matter just disappear into the black hole? It is because it runs into a surprising principle in physics called the conservation of momentum. The conservation of momentum was first described in 1670 by John Wallis, a mathematician. Newton, his contemporary, pioneered the idea a decade later. It states that if you have several objects, their collective motion, or their momentum, must remain constant. If a particle with momentum bumps into another particle that is still, and both bounce off each other, then the total motion of those two particles must equal the sum of the momentum of the first particle. There is no way to lose momentum. A rocket launched from a launch pad with zero momentum can only gain momentum by firing propellant in its opposite direction. Add the momentum from the propellant falling to the air and the momentum gained by the rocket moving up to get the net momentum of zero to your launch pad. This is a bit more than we expected. We humans are prone to stop and walk around seemingly obeying the law. This law can be observed if you consider all of the particles. Without a solid floor to push against, it would be difficult to move. The floor must have the same momentum as you. However, you don't notice the difference because it is much larger than you. Therefore, any momentum you give the floor does not affect its movement in any way. What does this have to do with falling into the black hole? Consider this next example. This time, it is about angular momentum. Imagine a ballerina who is holding their arms out and spinning on one point. Their momentum is created by the particles in their hands. They move a specific distance in a given time. They then tuck their arms under their bodies. What happens next? They suddenly spin much faster. This is an example of momentum trying its best to conserve. The momentum in the hands continues to move at the same speed as it did previously. It is now traveling a shorter distance but still moving at the same speed. Despite being closer to the body, it has less distance to travel for one revolution and completes it much faster. This makes the ballerina spin faster when she tucks her hands in and slower when she stretches her hands out. This is how it looks on a cosmic scale. Matter does not always fall straight toward a black hole in most cases. It will almost always miss it and start spiraling toward the center of the black hole as its gravity pulls it in that direction. It now has angular momentum. It speeds up as it moves closer to the center of the black holes. As it falls further down the gravity well, it gains more angular spin, much like a ballerina. Do you want to go a little deeper? You only need to spin faster. This matter, however, is not able to travel at the speed of light like the ballerina. The speed of light is the only thing that can travel faster in the universe. Einstein discovered this law. What happens to the spinning matter when it falls deeper into the black hole? It eventually reaches a point where it can't go faster due to the enormous forces and curvature. It has hit a roadblock. It cannot spin faster and cannot fall further into a black hole. This has many effects. As you can see, friction is created. All this matter spinning at such high speeds around the event horizon starts to bump into each other. This happens at very high speeds and can get extremely hot. The temperature of matter in a black hole's accumulation disk can reach 10 million degrees Celsius. It is enough to melt any material down to hot plasma. These constant collisions cause atoms to clench, and they give off more energy. It's like sucking a lemon. Their mass is reduced as a result. This gives off between 10 to 40% of an atom's mass in the form of energy. The energy then radiates across the universe. Nuclear fusion, which takes place in the Sun, converts about 0.7% of the mass into energy. For a moment, let that sink in. At 0.7%, the Sun shines brightly. What is the brightness of a black hole's disk of accretion? Quasars are the brightest of such disks and can shine at brightnesses exceeding 1,000 times that of all the stars in the Milky Way galaxy. It is possible to lose some of this momentum with the energy that has been left. You can shed more energy by transferring it to matter higher up in the accretion disk. Faster moving particles knock into slower particles just above them, giving them extra momentum and slowing down lower particles. This causes matter to lose its angular momentum and eventually fall into the black hole. One of the most striking characteristics of black holes and quasars is their jets. This can help to shed more momentum. Although we don't know everything about jets, including how they form or what they contain, only a few black holes have them. Current theories suggest they are caused either by magnetic forces created by the spinning disk or the rotational power generated by the black hole, which pulls up material from the disk and launches them into space. Due to all the moving, electrically charged particles, it is likely that magnetic fields will form as the accretion disk spins. These magnetic fields have such a strong and narrow shape that particles can escape through a narrow channel between the black hole's north and south poles. These magnetic fields could work in a similar way to rifling on guns. They channel particles down a narrow barrel. Even though particles moving at relativistic speeds can only go in one direction, we don't know why. They could be like steam from a kettle that is fired through the very narrow gap between the incredible heat and gravitational pressure. They go when they go. Relativistic jets can travel farther than the galaxies they originate from and are often millions, if not billions, of light years in length. PSOG 352.40341.3373 or 35215 is the name of a jet whose X-rays reach Earth from 12.7 million light-years distant. However, it only appears faintly because the radiation from such jets is extremely focused in one direction. It is possible to see faintly. Relativistic beaming, or the lighthouse effect, is a phenomenon that makes it difficult to see the beam if it is pointed away. Consider the famous M87 galaxy. Hubble clearly detects a relativistic jet in this image. This is the jet that is heading toward us. It is possible that there is another jet. However, we cannot see it as it is going in the opposite direction. This energy doesn't come directly from the black holes. Nothing escapes from a black hole. Instead, matter and radiation are generated by the accretion disk surrounding the black hole. Again, much of what we know about these jets remains theoretical. Although we can see them and even watch them move over time, we still don't know enough about them or what causes them. We don't know enough about accretion disks to fully understand how momentum conservation works. There is still a mystery as to where all that momentum goes. The sheer power of the accretion disks is undisputed. Einstein might have been wrong, but it is clearly possible to fall into black holes. It is possible to avoid falling into black holes, even though some of them are firing away material at them at relativistic speeds. You might not want to be too close to one if you consider the force of matter, which is millions of degrees heat and pushing at you as they try to lose its momentum. We've seen the amazing effects of a dark hole that can spread across entire galaxies. But it raises the question, how large can one black hole get? It is easy to find the largest black holes. All you have to do is look at large galaxies' centers. These black holes are supermassive and have grown in size since their formation many billions of years ago. They are constantly growing in mass as more matter falls into them. These supermassive black holes can have billions of times more mass than our Sun. It may surprise you to learn that the youngest black holes are also some of the largest. When we look at distant galaxies, we also look back in time. The galaxies that are billions of light years away often have the biggest black holes. The universe is 13.8 billion years old. Light takes billions of years to reach us. This means that the galaxy we are looking at can only be a few 100 billion years old from our perspective. That's quite young for a galaxy. It should be obvious that supermassive black holes closer to us, and therefore more massive, are larger because they have had more time to absorb matter. What's the deal? TUN 618 is the largest known supermassive black hole, and it has a mass of 66 million solar masses. Its mass by itself is equivalent to that of the Milky Way galaxy. TUN 618, however, is extremely far away. It takes light emitted from it 10.8 billion years to reach us. This means that we are observing it at the same time it was 10.8 billion years ago. It can therefore be as young as 2.8 billion years. Compared to this, the Milky Way, which is 13.6 billion years old, has a supermassive black hole at its core, Sagittarius, that is 4 million solar masses. Even though the Andromeda Galaxy's supermassive dark hole is larger, it still has only 200 million solar masses. It is important to remember that black holes can be difficult to detect and measure. This field of research is still very new since technology has only recently allowed us to begin observing black holes. Even then, it is difficult to see the black hole area, at least before the Event Horizon Telescope was invented. Even though the telescope can image one black hole in a matter of hours, our understanding is limited. Most of the distant black holes we know about cannot be seen due to their quasars. TUN 618 is a quasar. The black hole's disk is the accreting matter at an amazing rate. This causes it to explode into a quasar. Quasars are only able to sustain themselves as long as there is still matter falling into them. Otherwise, they will revert to dark black holes. Although it's difficult to understand the physics behind the accretion disk, it is believed that this friction is so strong that the quasar itself can produce thousands of times more light than all other galaxies. TUN 618 emits as much light as 140 trillion suns. It completely eclipses the galaxy in which it resides, so we cannot even see it from our viewpoint. Quasars can be seen very far away because they are among the most bright objects in existence. Malmquist bias is one reason why the largest black holes are so far away. This is because brighter objects farther away seem more abundant, while in reality, we can't see dimmer objects at that distance. It could be that supermassive black holes are distributed evenly throughout the universe. A galaxy may have a large black hole, but it is not a quasar. This means that we will not see it at a certain distance. We don't see black holes as large as the Big Bang. The universe is constantly expanding, and, as you might know, the matter was much closer together in the early universe. Quasars were much more common in the early stages of the universe because they require a lot of matter to emit light. The universe has expanded, and over time gas is transformed into stars. The largest stars can eventually become black holes or neutron stars, so they cannot be recycled into a gas again. A supermassive black hole will contain less gas than there is gas. This is the Big Freeze theory, which predicts that all of the universe's gas will eventually become black holes after trillions of years. We can see galaxies that have exhausted all their gas, so no new stars are possible. These galaxies are known as elliptical. Spiral galaxies can still produce stars because they still contain gas and dust structures. It's interesting to note that the most massive supermassive black hole appears to be located in elliptical galaxies. This is because there is not enough gas to fall into the galaxy's central supermassive dark hole. The gas must lose angular momentum. If that happens, The supermassive dark hole will likely be larger due to all the infalling material. This has happened with elliptical galaxies. However, it has not happened with spiral galaxies. Gas losing its angular momentum can be caused by the gravitational influences of nearby galaxies or collisions with other galaxies. Black hole growth is slower now that there is less gas in the universe than it was in the early universe. This could explain why there isn't a quasar within 500 million light-years of us. As the universe gets older, things become more chaotic and spread out, and so does the number of active cashiers. This means that the only quasars visible, including some of the largest black holes, are those that occurred a long time ago. What is the reason why the oldest supermassive black hole is often the largest? Although it may seem that way, this might not be true. Because we can see distant bright quasars, it is possible to measure them. Malmquist bias has not allowed us to find older and more distant black holes. As technology improves and more studies are conducted, we will begin to see a better picture of the universe. This is all you need to know about black hole technology. Are there any more things to learn about them? It's almost certain. One thing is certain, they have totally distorted my idea of what is normal in our universe. If you enjoyed this video, please subscribe, like, and share it with others. We wish you all the best, and we will see each other again.